Now I'd like to introduce Professor Ramesh Johari, who's today's featured speaker. He's an associate professor at Stanford University with a full-time appointment in the Department of Management Science and Engineering and courtesy appointments in the Departments of Computer Science and Electrical Engineering. He received an A.B. in Mathematics from Harvard, a Certificate of Advanced Study in Mathematics from Cambridge, and a Ph.D. in Electrical Engineering and Computer Science from MIT. He's the recipient of several awards, including the Okawa Foundation Research Grant, the MS&E Graduate Teaching Award, a National Science Foundation Career Award, and the Cisco Faculty Scholarship. He's also an associate editor for 2 journals, Management Science, for which he focuses on the area of models and simulation, and Operations Research, for which he focuses on information, games, and networks. And on that note, I will turn the floor over to Ramesh.
All right, thank you, Marcia. I'm really excited to be here. It's a fun thing to be able to present the material I'm talking about today. I think before I do that, I just wanted to give you a couple of words about myself. So I have a pretty diverse academic background in terms of things I've worked on. Recently, my 2 main interests are the design of online platforms. So I work a lot on things like, how Airbnb or Uber or Lyft should structure their platforms. And the other one is that I spend a lot of my time thinking about how organizations can make better decisions from data. And that's what I wanted to talk to you about today. So the topic of today's talk is A/B testing, which is the term that most of the tech industry uses for experimentation. I want to tell you a little bit about some of the problems that can arise when you use experiments in online settings, as we typically do in the tech industry and beyond. And also what we can do about it. So before I start, just one thing I should highlight. The work I'm talking about was actually done under my role as a technical advisor to a company called Optimizely, which is a large A/B testing platform. So they provide essentially a platform that allows other companies to run A/B tests on their sites. So I'll tell you a little bit about, first, what exactly is A/B testing, just to make sure we're all on the same page. So A/B testing is in the tech industry, for those of you who are in the tech industry, you've probably figured out that we need to have our own names for old ideas. And so A/B testing is nothing more than a new name for randomized controlled trials. But if you're in the tech industry, that'll always be referred to as A/B testing. And the idea is, as you can see in this picture, there's 2 variations in the most classic vanilla A/B test. In one of them, you've got a web page with a black Buy Now button. In another one, you've got a web page with a red Buy Now button. And you basically want to ask yourself, which of these 2 versions of the web page is better? Like, are people more responsive to a red button or a black button? So what you do is you take all the visitors coming into your site, split them at random between the 2 variations of the web page, and then just measure to see which one does better. And so the kinds of questions you might ask are which has a higher conversion rate. So A/B testing has actually been, as I mentioned, since it's essentially the same as randomized experimentation. It's been around for at least 100 years. But in the tech industry in particular, even there, it has a very long history. I'd say going back at least 2 decades in terms of its deep use across a range of applications. What's really interesting today is that we're kind of living through a period where the ability to run these experiments is being democratized quickly. And what I mean by democratized is that now sort of a typical employee at a business has the ability to run these experiments without really a lot of engineering or statistical knowledge. That's kind of what the point of Optimizely really was. It was to make it so that all you needed to know was a little bit of ability to code up a web page. And all you had to do was code up 2 variations of the web page, in this case, the black and the red button, and then they would take care of the rest. They would make it so that, all the visitors that are coming to your site are randomized between the 2 variations. They would take care of all the statistical computation to show you what was doing better or worse. So you really didn't need to know a lot. And I think if there's one point I can have you take away from what I'm going to talk to you about today, it's that as we live through this sort of democratization of statistics, I think how we use statistical tools and data scientific tools really needs to be completely rethought. The consumer of statistics and data science is no longer a statistician or a scientist. It's really everyone. But stats and science were not really developed in an environment where that was the case. So kind of what I'm fond of saying is that they have a bit of a user interface problem. And this talk is in part about that user interface problem. But it's really just the tip of the iceberg. I think there's a lot more to do here. So with that in mind, let's think a little bit about what exactly was going on 100 years ago when the foundations of randomized experimentation were first developed in statistics. So there's a phrase I'm going to use, which is fixed sample size testing. And you can see from this picture looks about as far away from the tech world as you could imagine, which is it's a picture of a farm. I think this picture is actually from Napa Valley, so it's not that far from the tech industry. But what we're going to talk about is really what the initial kind of setting was within which randomized experiments were analyzed, which is actually studying crop yields, and in particular the effect of fertilizers on crop yields. And so in particular, we're going to consider farmer Ron wants to test 2 fertilizers. The standard thing that you would have been told to do is to apply what's called fixed sample size testing, where the first thing you commit to in advance is how many plots of your land are you going to use to try to compare these 2 fertilizers. Okay, so that's the sample size. Next, you wait for a crop cycle. So essentially, you choose how many plots to use. In some of the plots, you apply one of the fertilizers, and others of the plots, you apply the other fertilizer. And you wait for the crop cycle, and then collect the data at the end. Okay? Once you've collected the data, you ask yourself a very basic question, which is a bit counterintuitive, but if you wrap your head around it using kind of the English description I put here, it's the easiest to understand. What are the chances that you would see the results that you saw if there was actually no difference between the 2 fertilizers? So when you put the 2 fertilizers into the 2 different groups of 2 different plots of land, you may see a difference in exactly what the crop yield is between the 2. And the question is, what are the chances that you would see the difference that you saw if there actually was no difference in the performance of the 2 fertilizers? So you may have heard the term p-value, or you may have used p-values, and this is what a p-value is. A p-value is literally the false positive probability. It's the chance that you observe the difference that you observed, or a difference at least as extreme as what you saw, even if there really was no difference between the 2. Okay? So in particular, when p-values are small, what that's saying is that it's really unlikely you would see the difference that you saw if the 2 fertilizers were actually the same. And what we typically say about that is that then we can reject the hypothesis that the 2 fertilizers are actually the same. Okay? And that's kind of how we argue that there's a difference between them. So in particular, what does small mean? A typical cutoff in industry would be something like 5%. So if the p-value is below 5%, we declare the result statistically significant. Right? And then we can say there's a difference in the 2 fertilizers. So this is a really powerful approach. And one of the reasons it's so powerful is that it actually does something much stronger than just dealing with controlling false positives. So one thing you can see from this is that if you cut off the p-value at 5%, one of the things you're saying is that you're not willing to tolerate more than 5% false positives. All right? But the second one is that, in fact, what it's doing is it's optimally trading off your ability to control false positives against the detection of true positives. Because you can see, like, one way that you can control your false positives is to never declare that there's a difference. So you run this experiment, and no matter what you see, you declare, I think the 2 fertilizers are the same. So that's a world in which you'll never have a false positive, but it's just because you never declare anything positive. And the problem with that is that you're never going to find a real difference. So, in all statistical testing, what we're doing is we're trying to balance controlling false positive results with finding as many true positive results as we can. And what's really neat about this approach is that, in fact, it does that. It actually optimally balances true positives and false positives. It does it essentially as efficiently as possible. And then I wanted to highlight one other really valuable thing, and I think this is why p-values are so prevalent in the A/B testing world. It's cool that you can summarize the entire experiment through just this one number, which is the p-value. And one thing that's nice about that is, different people might run different experiments. There might be different statistical properties of the experiments that they run. But at the end, if what you produce is a p-value, then all I need to do is apply this simple rule in bullet 4, the p-value, cut off the p-value at my desired control on false positive probability. And I know that I've got this optimal trade-off between true positives and false positives without having to really understand anything about what went on inside the experiment itself. And so p-values, the way we like to talk about this is that they have kind of a transparency and a portability to them that allows organizations to share results from multiple experiments across people using kind of a simple statistic of a p-value, okay? So that's a very valuable thing about p-values. Now that said, I'm going to guess that many of you have probably read things in the popular press that suggest that p-values are a kind of measure under great scrutiny. There's been a replication crisis in psychology where people are kind of concerned that results that are published in journals are not reproducible, and this is kind of highlighted. It's put a lot of attention on whether the use of p-values and the way we do it in the scientific literature is actually reasonable. You know, I don't want this talk to be a defense of p-values necessarily, but I think what I'd like to ask us is, given some of the pitfalls that arise in A/B testing, can we adapt p-values to be something slightly different to address those pitfalls, right? So now let's get into that. What are the pitfalls of using p-values in A/B testing today? And for that, we really need to compare what the difference is between running randomized experiments on a website and running a randomized experiment, you know, on crop yields. So in 1916, and Farmer Ron actually was an allusion to Ron Fisher, who was kind of the father of experimental statistics, the way that I described it to you. In 1916, I think two characteristics that are important to highlight. One is data was really expensive and really slow. So you had to commit these, you know, plots of land to run your experiment on, and you just had to wait an entire crop cycle to run the experiment. There was nothing else to do. You know, just go grab a cup of coffee and wait around until you get your results. The other thing is this point that I highlighted at the very beginning, which is that in 1916, if you wrote up a stats paper, or you wrote up your results using statistical analysis, the person you were giving it to was a trained statistician. So you didn't have to worry about whether they were interpreting a p-value correctly or drawing the correct inferences from the dashboard that you showed them. Today, we're in a completely different environment. Data is super cheap and real time, so it's coming in very rapidly. You can decide on the fly to kill an experiment, to start a new experiment. And then the other point that I made at the very outset, which is that everybody is a practitioner. You're a practitioner. You know, you may not even realize it, but many of the things that you're doing today in your job will be A/B tested in some form within 10 years. You know, if you think about logistics, or you think about healthcare, or you think about, you know, just about any industry, there are so many different points in these different disciplines where it's possible to introduce some of these statistical methods of A/B testing to make better decisions. So we're going from a world in which practitioners were trained statisticians to one where really everybody is going to have to be doing this kind of work even if they weren't trained in it. So, you know, what that obviously highlights then is we need to ask ourselves, how are you different from Farmer Ron? All right, you being the prototypical user of A/B testing today, how are you different from Farmer Ron? All right, so the first one is that time is money. Now, because data is cheap and plentiful and experiments can be started and stopped on the fly, you want results as quickly as possible. Okay, so that's going to be very important. That's something I think that while Farmer Ron might have wanted results as quickly as possible, he didn't have much of a choice except to wait for a crop season. You have a choice. You can actually choose to stop. And because you can choose to stop, what you're going to do is continuously monitor the results that you're getting from the test and use those to decide whether or not you want to continue. Okay? And in particular, you're going to use the dashboard to tell you when the results are significant, and that's probably the thing that's going to guide your decision on whether to stop or keep going. So this, in contrast to what I called fixed sample size testing, is what's called adaptive sample size testing. You adjust the test length in real time based on the data coming in. Okay? So I hope that's clear to everyone. There's a huge difference between what I just told you here and what Farmer Ron was doing. Farmer Ron had committed to a fixed sample size at the beginning, largely out of necessity, because there were a fixed number of land plots that he's going to work with, and he had to wait an entire season to wait to get data back. You, on the other hand, are in a world in which data is coming in real time, and therefore you're given the ability, the opportunity to adjust the test in real time, okay? Or adjust the experiment in real time. And in particular, you know, what's fascinating about this is it's not just that you have that ability. It's actually that we encourage you to use the ability. So here's a sample results dashboard from Optimizely. And I want to call out a couple things about it. So in this dashboard, what's going on is there's actually 3 variations that are different from the control, not just one. So it's variations 1, 2, and 3, and then the original is the control. And then there's 3 metrics of interest: views, example click, and pick click. And so those 9 boxes, you know, that go from views to pick click and variation 1 to variation 3 are all comparisons on that metric of that variation against the control. And, you know, the green and red are telling you where the dashboard thinks you have significant results in the positive or negative direction. But what I want to highlight for you are these huge numbers on the left-hand side, unique visitors and days running. Those are like counters that are ticking forward that are basically telling you, hey, here's how long your test has been running. Every time you log in, we're trying to remind you that time is money. We're showing you that, you know, time is elapsing, and here's the results you have, and you're being put in a position where you're always being asked to trade those things off. So we're kind of forcing you into an adaptive sample size testing mentality just by the design of the dashboard. And the other thing that I want to highlight is this little blue link that says, how long should I run my test? Now, if you click on that link, what that brings up is a sample size calculator, which essentially tries to get you to think, how much longer should the test be running? The great irony is, this link is on the results page, which means I'm having you think about how long you want to run the test once you've started the experiment. Now, contrast that to Farmer Ron. What we said about fixed sample size testing is Farmer Ron is asked to do that before he ever runs the experiment. And indeed, if you look in any textbook on experimental design, that's one of the first things you'll learn is commit to the sample size before you run the experiment. So when I started working with Optimizely, this is one of the things I found most fascinating is that this link, how long should I run my experiment, was on the results page, not on the experiment design page. All right? So here's a thought experiment, and I should have set this up as a poll, and I didn't. So I'm just going to ask you to commit to what your answer is. Here's a thought experiment that's going to help you get some insight. Okay, and I assure you this is not a typo on the slide. Suppose 100 individuals run AA tests. So that's not a typo. What do I mean by an AA test? If you're a customer of Optimizely, one of the first things you want to figure out is whether Optimizely is actually doing what they said they would do. And one of the ways that you might test that is to run an experiment where you know up front that the control and the treatment are exactly the same thing, that the original and the variation are the same. Okay? So that's what's called an AA test, and the reason it's called an AA test is at least in that case, you know there's no difference from the beginning. So it's like a diagnostic. You can test, when Optimizely tells me that they're going to help me find real differences, is that what they're really doing? Okay? So what do? You run this AA test, and now you monitor the dashboard that I showed you on the previous slide, and you just keep looking at it every day, and you wait for the first time that the p-value drops below 5% in this AA test, okay? Which means you wait for the first time that the dashboard tells you that the data that you're seeing is unlikely if there was really no difference, right? And let's say we do this up to a maximum of 10,000 observational units or 10,000 visitors to my site, okay? So the question is, how many people find a result and stop early? Right? How many people find a significant result and stop early? So I'm just going to step through a few potential values here. Let's make sure that we all understand if this is working as it's intended, then no more than 5% of you should find a significant result and stop. Because what we're saying is that any result here that's declared significant is a false positive, right? There's no difference between A and A. So if I declare that there's a difference, that is a false positive. I'm saying they found a difference when there wasn't one. So anything that's found that's significant is a false positive. When we use a 5% cutoff on the p-value, what we're saying is we don't want more than 5% false positives. So nominally, 5% is what we should expect. So, I can tell you I've run this survey multiple times, and, I climb up from 5%. I ask everyone to put their hands up and then climb up from 5% to 10% to 20%. And the hands stay up. And when I get to 20 to 30 is when most of the hands drop. And then you get up to 40%, 50%, and there's basically nobody left. And 60%, nobody left. Well, it turns out the right answer is actually close to 60%. Over half of these individuals are going to find a significant result. Now, I want you to stop for a second to understand what this means. It means, you're a data scientist in a company. Your boss is asking you to use an A/B testing, methodology. You decide to test out your methodology by running an AA test where you know there's no difference. And out of half of the AA tests that you run, you discover that there's a significant difference. So essentially what that means is A/B testing would be completely useless if that was the case. It would mean that 1 out of 2 times that you ran an experiment where there was really no difference, you're declaring a difference. In which case, what's the point? You might as well just flip coins to decide what to do. There's no point of actually running experiments. Okay? And so the first point here, and I understand that up to now I haven't explained to you why this is happening, but the first point is, in A/B testing, peaking can dramatically inflate the number of false positives that you get. Now, what is peaking? Peaking is watching the dashboard continuously and deciding to stop the first time you get a significant result. Okay? So let's try to understand why that's happening. All right? And that's kind of the crux of this talk, is exactly what is causing this problem. I mean, you might imagine that it shouldn't matter that I'm looking at the results, right? Because whether I look at them and do something, whether I look at them or not, it doesn't matter. The data is the same. So the problem isn't really the looking. The problem is the doing. In particular, what do I do after I look at the results? All right? So remember, Farmer Ron had committed to a fixed sample size at the very beginning and only looked at his data after that sample size was done. You, on the other hand, are choosing to look at your data every single day and waiting until the first time that you see the p-value drop below 5%. That's the big difference, is adaptive sample size versus fixed sample size. So what's happening is, and let's look at the sample run of an AA test. This is actually from Optimizely, right? if you look at the sample run, it's an AA test, right? So what we would expect, oh, and I should tell you what's being plotted here is actually 1 minus the p-value. So when this graph is high, that means the p-value is low, okay? And so what you observe here is that very early in the test and late in the test, there are 2 points at which the 1 minus the p-value crosses 95%, or equivalently the p-value falls below 5%, okay? This is despite the fact that it's an AA test, and this graph actually was this is the type of thing that was the basis for many customer support calls to Optimizely. Now put yourself in the shoes of the poor customer support rep. They take the call, and the person on the other line says, hey, you know, I just ran this AA test, and I'm getting all these significant results. Like, what's going on? And you know, in customer support, you're typically left to explain that maybe there's a bug in the platform, maybe they're not using it properly, they should look at a knowledge base article. And the reality is, you know, they were in a tough spot. It's like not clear what to tell this person because this actually is, there's nothing wrong. There's no bugs. This is what the data is actually doing. And so what's going on is that when you watch the p-value over time, then you allow yourself a lot more opportunities to decide whether or not something is significant. Farmer Ron only had one opportunity, the very end of the experiment. In your case, you're looking at it after 100 visitors, after 200 visitors, after 300 visitors. So you have all these different opportunities to conclude whether or not something is significant. Well, obviously, if you give yourself more chances to decide if something is significant, that increases the likelihood that you're going to find a significant result. And that's exactly what's happening. In particular, if you're allowing yourself to continuously watch the p-value, and if you're willing to wait long enough, there's actually a high chance of a result that's eventually inconclusive, which in this graph it is, looking significant at least 1 point along the way, okay? Said differently, if I'm allowed to just keep watching the p-value over time, let's suppose that it's true that eventually only 5% of these experiments, of these AA tests, are going to have a p-value that's below 5%, so are going to have a false positive. Even if that's true eventually, a huge fraction of them, in fact, a majority, are going to have a p-value that's less than 5% at some point along the way. Okay, so that's the difference. And if you allow yourself to keep looking, you're going to pick up on that, all right? So here's the kind of technical issue, and I want to highlight now, there's going to be a couple points in the talk where I do a deeper dive on the technical side. This is one of them. So one way to think about what's going on in fixed sample size testing, if you unpack what that p-value less than 5% rule really amounts to, a different way to think about what's going on is you look at the observed difference in sample means between the control and the treatment. So I measure the sample mean conversion rate in the treatment group, the sample mean conversion rate in the control group, and I take the difference of those two, okay? Now, it's a well-known kind of fact in probability that, you know, when you've got n samples of something, the central limit theorem or you know, a lot of other techniques will tell you that kind of the spread of the sample mean is going to look about like 1 over square root of n, okay? So if you think about what the sample mean looks like, it goes down like 1 over square root of n over time. So if I want to declare that there's a significant difference between control and treatment, typically what these rules involve is saying that you declare significance if the difference of those two, and on the left-hand side there should have been an absolute value there actually. It's not just the raw difference, it's actually the absolute value of the difference. The absolute value of the difference exceeds sort of a multiple of 1 over square root of n, then we declare it to be significant. Now how do we choose that multiple? The multiple is based on the significance level. So in this case, like we had a 5% significance level, that would dictate what the constant in the numerator looks like, right? So this is kind of a convenient way to think about what we're actually doing because I find that it's more intuitive to think of sample means rather than p-values. You can actually interpret what the sample mean is going to look like. And the more samples you get, the lower the spread in the sample mean is going to be in its uncertainty. And so this is a way that we declare significance, okay? Now here's the problem, right? So what we're saying is, in fixed sample size testing, you declare significance if the difference of sample means ever, you know, if it exceeds 1 over square root of n at the chosen fixed sample size, okay? But in probability, there's a classical result that says that difference of sample means exceeds not just constant over square root of n, but actually log n over square root of n, square root of log n over n, for infinitely many n. Now, practically speaking, what this means is that if you're willing to wait long enough, and your rule is that you declare significance anytime the difference of sample means is bigger than a constant over square root of n, you're guaranteed to eventually do it, okay, if you're willing to wait long enough. So this basically says, I mean, I could have asked you a different question, which is imagine that every one of those 100 people waits indefinitely to ever see if the p-value drops below 5%. And what this result is saying is that every single person would eventually declare a significant result. So your false positive rate would be 100%, right, which is much worse than even the majority that I was giving you a second ago. So thinking about it practically, if you think about what the effect is in real data, on the x-axis in this graph, what I have is the number of observations in the experiment, so it goes up to 10,000. And on the y-axis is the false positive probability, and the three different curves are the false positive probability I see up to that sample size if I use these different cutoffs for the p-values, so 1%, 5%, or 10%. And so in the thought experiment we did, I was showing you alpha of 5%, or a cutoff of 5%, up to 10,000 observations, so that's kind of the final point of this green line. But you can see that in all of these cases, red, blue, and green, there's massive inflation over what the nominal desired false positive probability was. So for example, if I use a 1% cutoff, then I still get an inflation up to like 21%, 22% false positive probability when I have 10,000 observations. And that means that I'm essentially getting a 20-fold increase in the number of false positives because I'm doing this thing of peaking at my experiments. Okay? So the point is if you just think about the incentives, right? As a practitioner, there's huge incentives to find significant results because that's how you're judged. Your boss wants you to say, yeah, hey, look, I ran this test and I got this amazing result, right? So you can have these organizations where people are running experiments and finding significant results all the time, only to discover that most of them are spurious and kind of, not meaningful. Okay? So I guess what I like to ask then is, are there irreconcilable differences here? I mean, what would the user like? The user wants to choose to stop adaptively, to trade off the test length against the detection of true positives. And at that time, if the p-value is small enough, the result's declared significant. Okay, so that would be like essentially that the user wants to use adaptive sample size testing. They want to be able to look at that graph I showed you of an AA test and then stop whenever the first time that the p-value looks small instead of being committed to a fixed sample size. On the other hand, what I told you about fixed sample size testing is that it optimally balances false positives and true positives, but it's not adaptive. What I told you about adaptive testing is that it massively inflates false positives. So what are you supposed to do? How do you balance between these two things? What's the resolution of the irreconcilable differences? Okay. Well, there's really two views on this. One of them I got by talking to colleagues at Stanford, and in the Safe for Kids version, it's called the RTFM approach, which is read the frickin' manual approach. And, all right, what does that mean? Well, when I asked my colleagues, they were like, wow, that's incredible. If they would just pick up a stats book, they would see that the right way to run an experiment is to commit to the sample size in advance. And then, the usual sort of ivory tower comments regarding the fact that, practitioners don't know what they're doing, and they should all take stats classes or data science classes. And that's, I think I am an academic as well in the ivory tower, so I'm sort of prone to thinking this way myself at times. And, initially I was kind of sympathetic to that. I'm like, okay, I'll go back to Optimizely. I'll just tell them, hey, why don't we just put up a tutorial that says, like, commit to your sample size and don't peak, right? But then we sat back for a second. What we realized is this makes no sense. The reason that users are peaking is because they can. So we're basically telling you, you're using a platform where you get data in real time, but I don't want you to take advantage of the data in real time. I want you to sit back and turn off your computer, go get coffee, wait like Farmer Ron would. Essentially, I want you to drop yourself back 100 years in your practice so that you're not taking advantage of all the data you get in real time. Now, when you put it that way, it makes no sense, right? And that brings us to kind of like the first maxim of good product design, which is the user is always right. So what you don't want to do is you don't want to commit to saying that your methodology is right and the user is wrong, because usually when the users consistently have a certain behavior, there's a good reason for it. And in this case, it's because the data is actually coming in real time. So users are right, they have good reasons to be adaptive, and our goal should be to change what we're doing to fit a natural user model, and one which is consistent with real-time data. So that's this point about user interface design, which is like, think of p-values as a user interface. The point is not that users are using the current p-values incorrectly. The point is we've designed the wrong p-values for the way that users want to make decisions from real-time data. All right? And so that brings us to how we reconcile, what we're doing with what users want to do. And the approach is really just change the p-value to account for the fact that people continuously monitor. So basically what we want to do is allow users to continuously monitor the test, allow them to choose whenever they want to stop based on the p-value that they see, and really what we want is what's called an always valid p-value. No matter how the user chooses to stop the test, we want to guarantee them that there's no more than a 5% false positive probability. Okay? By the way, I saw one of the questions here is there any significance of the value of 5%? And I just want to point out I've been using 5% as an exemplar throughout the talk, but it's not really, consequential. It could be 1%, 10%. It's really just that number is whatever your desired control on false positive is. Okay? So, what we want to do is we want to report this always valid p-value and make sure that no matter how the user chooses to stop the test, there's no more than a 5% false positive probability. And in our solution, what we do is we provide a near optimal balance between test length and detection of true positives while controlling false positives and allowing the user to be adaptive. All right, so we're getting that near optimal balance between true and false positive rate that we got from fixed sample size testing. We're controlling false positives, and we're allowing the user now to be adaptive. So this is the reconciliation that we wanted. Now, how are we doing that? Again, the crux of all of this rests on choosing the right p-values. Okay. So what I'm going to do is walk you through just quickly, and I think about like 10 more minutes. Does that sound right? Yeah. So I'm going to walk you through quickly. It's a little bit technical, but I'll just walk you through quickly how we do this. And there's a lot more details available through some of the papers that we've written on it. So remember what I told you, which is that what we do is we wait for the difference of sample means to cross 1 over squared of n, or a constant over squared of n. That's going to happen infinitely often, even under what's called the null hypothesis, even if there's no difference between the two treatment and control. Okay? So that's a problem. What we want to do, if we're going to become more conservative, allow the user to stop whenever they want, we need to pick a stopping rule, or a rule that declares there is a significant result that's kind of more conservative than constant over square root of n. And what we do is we pick a boundary that instead looks like a constant times square root of log n over n. Okay? And in particular, now let's ask the question, what is the chance that the difference of sample means will ever cross a boundary that looks like square root of log n over n times a constant? It turns out that that is actually a bounded probability, which means that even if there's no difference between the treatment and control, the chance that you ever cross the boundary constant times square root of log n over n is actually bounded. And in particular, by changing the constant, I can change that probability. So if I want to do is control false positives, then I could do it the following way. You give me your desired false positive probability control, that's what I'm calling alpha. I will spit out a constant c of alpha, such that if you stop the first time that your difference of sample means crosses c of alpha times square root of log n over n, you will only make mistakes a fraction alpha of the time in cases where there's no difference. So your false positive probability will actually only be alpha. Okay? In words, the chance the boundary is ever crossed is no more than alpha, and this should have additionally if there is actually no difference between the treatment and control. So it's a bit technical again, but the real point here is like what I'm doing by forcing the difference of sample means to be larger before I reject the null hypothesis is I'm becoming more conservative. Okay? And essentially that's the rule that we use. It's not exactly this, but it's approximately this. And what that rule kind of is doing for us, it's what's called a sequential test of power 1. So this rule, stop and declare significance when constant times square root of log n over n is crossed, is what's called a sequential test of power 1. And it basically has two properties. One is it controls our false positive probability at level alpha. So like if alpha is 5%, then I'm guaranteeing myself that I won't reject unless the sample mean, if there's no difference between the two, the chance that I make, that I declare significance is no more than 5%. But it also has the property that if there is a real difference, eventually I'll find it. Because if there is a real difference, eventually square root of log n over n goes to 0. And so eventually the sample mean will actually cross, the difference of sample means will actually cross that level. You can see this better in the picture. There's 4 curves in this picture. The blue and the red are basically these curves that look like constant over square root of n. So what you want to be thinking to yourself is the sample mean, the difference of sample means, is something which is moving around in the y dimension here as the number of observations increases. If the difference of sample means ever crosses either the blue boundary for a 10% cutoff or the gold boundary for a 5% cutoff, you declare significance using the fixed sample size testing model. Okay? Now those boundaries are fairly low, which means even a small difference of sample means is enough for you to reject and declare that there's a significant result. Okay? To stop and declare a significant result. And what I had pointed out to you earlier is that this green curve, which is the law of the iterated logarithm, that looks like square root of log n over n, is actually guaranteed to be crossed infinitely often. And you can see the gold and the blue curves essentially lie underneath the green curve, with the exception of some region at the very beginning for small sample sizes. On the other hand, this boundary square root of log n over n that I just explained to you lies way above the other three boundaries. And that gap, that additional gap there, is what's essentially allowing us to ensure that even if you continuously watch the difference of sample means over time, the chance it ever crosses the red boundary, even if you were to wait indefinitely, is bounded by either 5% or 10%. I should say the red curve here is actually for the 5% setting, and then the curve for the 10% setting would be a little bit lower. Okay? So those are kind of the technical details. And, you know, kind of giving a little bit of homage where homage is due, the rule that I just described to you is what's called the mixture sequential probability ratio test. It was actually developed here at Stanford by Herb Robbins and David Sigmund. Sigmund is still here. Robbins passed away, and you know, both kind of very well-known statisticians. So here's how we use it to get p-values. You basically define t of alpha to be the stopping time of a test that stops when your desired false positive probability control is alpha. Of course, it'll be later when you have a tighter desired control on false positive probability. And I define the p-value at time n to be the smallest value of alpha such that the corresponding stopping time for that level of alpha has already gone by. Okay? Where if that was the desired alpha that I wanted, I would have already stopped by now. So the p-value is the smallest alpha where I know I would have already stopped by now. Okay? Well, it turns out that with that definition, the first time that the p-value ever falls below alpha is actually t alpha, which means, in words what this means, is if you follow the rule of stopping the first time the p-value goes below alpha, then what you're doing is you're just recovering that stopping rule that I just developed. Okay, and so in particular, you're going to be finding a rule that controls your false positive probability at level alpha. Okay, so it has false positive probability bounded by alpha as desired. More importantly, the same thing is actually true for any adaptive stopping rule that the user might choose to use, even if they don't want to stop the first time the p-value falls below alpha. No matter what they do, their false positive probability is controlled by alpha. Now that requires a little bit of reasoning, and I'll skip past the proof of that. But that you can kind of easily work through from what the definition was on the previous slide here. Okay, so from the definition of the p-value, you can actually show that no matter how the user chooses to stop, their false positive probability will never be larger than alpha, than their desired alpha. Okay, so you know what I want to try to convince you of, the last thing I want to show you on this front is that not only are we controlling your false positive probability, we're actually doing a really good job of helping you find real effects. And to do that, what I want to do is go back to the Optimizely platform and compare what we're doing against fixed sample size testing. So I need to make sure I do an apples-to-apples comparison here. And to do that, one of the things I need to explain is that when you do fixed sample size testing, in general, you need to estimate the effect that you want to detect in advance because you're committing to the sample size in advance. So this minimum effect that you care about detecting is going to be what dictates how long how large your experiment needs to be. And that minimum effect is what's called the minimum detectable effect. So what we do is we go through the following procedure. We took 40,000 experiments on Optimizely that had run for a really long time. So we kind of assumed that the effect that we're seeing at the very end of the experiment is the real difference between the treatment and control in these experiments. And for each of them, what we do is we consider what the fixed sample size run length would be if we had correctly estimated in advance what the effect in the experiment is going to be, if we underestimated the effect by 30%, if we underestimate the effect by 50%. 30 and 50% are not that big, by the way. What I mean by this is, like, imagine the conversion rate difference in treatment and control is like 1%, and that's the real difference. Underestimating that by 30% means that I actually believe it's, you know, something like 0.7% difference, and underestimating by 50% means I think it's 0.5% difference, which when you're measuring differences as conversion rates, this would be well within a margin of error of what you believe is going to happen. So, you know, obviously the fixed sample size testing here has a huge advantage because I'm feeding into it what I observe to be the final difference in conversion rates at the end of these experiments that we had historically. So in reality, I won't have access to that. And in particular, the test that we're using, the way we're developing p-values does not assume we know anything in advance about what the effect is actually going to be. So what is the consequence? So in this graph, what I'm showing you is the relative run length of the test that we developed against what you would get if you used a fixed sample size procedure. And the first graph I want to draw your attention to is the fully dotted graph, the one that's most spread out. And that's the case where we find a fixed sample size that gives us 80% detection of true positives And then we compare how long our test, our newly developed MSPRT test, takes to run against that fixed sample size. And what you can see here is often it is no more than 1x the run length, but sometimes it's 2 or 3x the run length. The x-axis here is measuring kind of how large is the continuously monitoring adaptive sample size method relative to the fixed sample size. And so sometimes it's 2 or 3x even. So that doesn't sound that great. But part of the reason for that is because we favorably biased the fixed sample size calculation. We fed into it exactly what the correct sample size would be, or what the correct effect would be. What I want to draw your attention to instead is the solid line, which is what you get if you underestimate the MDE by 50%, and then compute a fixed sample size for that. And what that does is it makes you compute a much longer fixed sample size. As a result, when you're adaptive, you do much better. And then what you're seeing is that more often than not, you stop in a time that's much shorter than what the fixed sample size would have been. So in general, kind of this is like a tip of the iceberg that shows you that you're able to get kind of really good detection of true positives in good time, but still control a false positive probability despite the fact that you're being allowed to continuously monitor the experiment. Okay, so kind of the high-level takeaway from all the technical discussion is that we're developing a procedure to change the p-values so that you're allowed to continuously monitor the test, still get really good detection of true positives, and yet control your false positives. Okay? I'm going to wrap up because I'm nearly out of time here, just by mentioning one other thing that I think is important to deal with, which is what's called multiple hypothesis testing. And the point is just that if you remember that dashboard that I showed you, if there's really no difference in any cell, right, then you can ask yourself a question like, what fraction of the cells that I'm looking at, variations and metrics, will have p-values less than 5%. I'll see a green when it's up, a red when it's down, a color when it's significant, when the p-value is less than 5%. Well, what I'm saying is that if there's no difference between any of these, between treatment and control in any of these cells, then I should only see about 5% of them popping up as positive. But if I'm running a lot of variations, looking at a lot of metrics, I'll have a lot of cells in my dashboard. So imagine I have 100 cells in my dashboard. This is saying 5 of those cells are going to pop up as being significant just due to random chance alone, even if there are no differences. Now, our vision is drawn to the significant results, right? And we're coloring them green and red. And that's a real problem because what it'll mean is you're getting a lot of false positives and then drawing all your attention into the false positives. Instead, what you typically want to do is you want to be a little bit more conservative when you run a lot of hypothesis tests to make sure these false positives are not polluting your dashboard, so that when your attention is drawn to the green and red, really you don't have a lot of false positives mixed in with the greens and the reds. And this is what multiple hypothesis testing is. I'm going to skip this slide. I just want to say kind of in words that in addition to what we did to control peaking, in the Optimizely dashboard, we actually implemented corrections for multiple hypothesis testing so that people are able to draw more meaningful inferences from these environments where they run many variations and many metrics. Okay? So, like I said, this is only the tip of the iceberg of the stuff that there is to learn here. I teach a class in the fall called Small Data, MS&E 226, which, really the reason it's called Small Data is it's everything except big data. And the point of that class is really to give you the conceptual foundations to help you think about what to do in this kind of brave new world where A/B testing, other tools like it, are democratizing access to statistics and scientific inquiry in virtually every industry. And so what you really are going to need to do in that environment is become an effective conceptual communicator of exactly what the data is really saying within the organization, and also you're going to need to set norms for how the organization uses data so that you don't make poor decisions, kind of like what I've been talking about here. Lots of other things that we've done in this regard, but I'll stop there and turn it back to Marcia.
Great, thank you very much, Jimmy. That was a perfect introduction to A/B testing and a lot of extra detail as well. So we've got some questions in. We still have time if you want to send any others, and I'll now hand back to Ramesh so he can tackle some of these.
All right. So I think, just given the time, I want to make sure I pick kind of a breadth of questions here. So one question I want to try to get into, there's a few different questions that ask about kind of the relationship between adaptive and fixed sample size. When would you choose one over the other? Now, thinking about it at a high level, one thing I want to point out is that you're basically always better off being adaptive at some level, or you shouldn't be any worse off, right? Because one thing you could do when you're adaptive is just wait until whatever the fixed sample size would have been and stop there and then look at the data. So you're kind of strictly increasing the range of things you can do. You would imagine that shouldn't leave you worse off. The reason it leaves you worse off is not because you became adaptive. It's because the method by which we choose to stop or declare significance once we become adaptive is sort of flawed. So, I guess what I would say is that in general, our goal should be to be building platforms which allow users to become adaptive and do at least as well as they would have done using fixed sample size methodology. In terms of how to choose, really the point is that we live in an age of real-time data. And in the age of real-time data, I think adaptivity is going to be the wave of the future. There's no reason to commit. So it's kind of funny, I've come full circle here from when, I was asking my colleagues and they're all like, oh, just read the stats book, it'll tell you commit to the sample size in advance. I guess what I'm saying is we need like sort of a different vision on that. In the 21st century, the stats book should lead by saying, imagine your data is coming in real time and you want to choose how long you run your experiment adaptively. A couple other things I want to mention. Someone asked about, why not use a Bayesian approach? And I think this is a great question. It would take a while to kind of set up the background to what it means to be Bayesian here. At a high level, what it would mean is that I start with some belief about what I think I will see in the experiment. That's called a prior. I get the data and I update my prior belief to what's called a posterior belief, which sort of is a combination of what I believed when the experiment started plus the data I received. What I want to point out is that there isn't really much of a difference between being Bayesian or not, in at least the method that we implemented. One of the ways that this method works is it requires you to sort of average over all possible values for that difference between the treatment and control that you think could be observed. And that averaging over all of them, it turns out that has a very close connection to this notion of a prior distribution in Bayesian statistics. So I'll kind of leave that as a teaser. I do spend at least one lecture in my course in the fall talking about the role of Bayesian inference and how it contrasts with things that are done in practice. I think I would also add to this that my understanding and my own personal belief is that practitioners are woefully undertrained in Bayesian methods in modern data science. I think like lots of organizations would benefit from using all the past data they have to build prior beliefs, and that hasn't really been happening as extensively as I would like. So this is a major area of research emphasis for me. And then finally, the other thing I want to mention here is, this is totally self-serving, but somebody asked me to briefly describe how the correction of multiple hypothesis testing works, which is great. As an academic, you never love more when you get a question that lets you continue your talk. So that's what I'll do. On multiple hypothesis testing, kind of the main point is this, right? Like, let's ask what is the problem with getting 5 out of 100. Let's say there's 100 cells in that matrix where I have variations in metrics. And of those, there's no difference in any of them, and I declare 5 of them to be significant. The problem really is, like, imagine what you'll show your manager. They'll want to see the dashboard for the test. In that dashboard, they're going to see 5 things that look red or green. Their eyes will be drawn to that. They'll want to spend a lot of time understanding what happened. So what's happening is we're spending all our time zooming in on these cells that look significant. So what we're trying to do when we apply multiple hypothesis testing corrections is we're actually trying to say within the cells that look significant, we don't want too many false positives. So this is what's called the false discovery proportion, which is we want the fraction of false positives among those that we declare to be significant to be bounded by something small, to be, say, less than 5%. And the control of that in average is what's called the false discovery rate. Basically what the procedure amounts to is declaring significant those things that sort of, generally speaking, have smaller p-values. So p-values that are larger and closer to the cutoff will be less likely to be declared significant. The details of it, it's what's called the Benjamini-Hochberg procedure, and that's something that you can kind of learn more about. It's a very simple procedure using the output p-values. It's something which even the Wikipedia page does a pretty good job of describing. And I talk about it a little more in 226 as well. Okay, and then let's see, a couple other things. One question about computational issues. So what's really cool is, actually a couple questions about this. So what's really cool about the methods we developed is they're not algorithms, they're formulas. So in terms of implementation, all of the computation of these p-values can actually be done client-side in the browser. It's super fast. You can actually get the formulas if you want from, like I said, these technical reports that are online, either through Optimizely or by looking at the research papers on the topic. I think in particular, this is a really important consideration in the world of streaming data when data is coming in real time. Any dashboards that we build for people to be able to continuously monitor experiments do have to be able to work with data in real time and deliver sort of the computational results in real time. One advantage of what we've developed is that it's as easy as kind of classical p-values were, which also could be easily computed in a streaming format. I do think that as we move to more complex methods, this would include like Bayesian methods, some methods like multi-arm bandit algorithms, the computational issues do really come to the fore. And I think this is an interesting area of research right now. There's an intersection between designing the user interface, designing the computational methods to relay statistics to the user, and then actually processing the data coming in real time on the back end. So you've got infrastructure, you've got algorithms, you've got statistics that are all coming together to deliver these tools for people to make good decisions from data. Let's see, maybe one more question? Does that sound good? Or do we, I'm wondering how much more time? Can we keep going? Okay, cool. So I'll take a few more then. So, oh wow, there's some really good questions here. So I guess one of the things I want to talk about is, there's a question that says, what's the best way to conclude that stopping a test early doesn't really, that a test early on doesn't really have any difference, right? So this is basically saying, like, if you're looking at the data coming in real time, and one of the questions I used to love, I took a lead from Stanford to go run a data science team in industry, and one question I used to love was, how long do I have to wait to get statistical significance? I mean, you just think about what that question is asking. It's taking all the methods of fixed sample size testing and completely blowing them up, because you're going back to the data science team and asking them regularly, like, how long am I going to have to wait? What's really going on underneath that question is, again, people care about how long they're running a test. They want to know how likely is it, based on the data that they've received, that there really isn't any difference here, even if they were to wait longer, right? I mean, I guess my answer to the question, what's the best way to know that, is that the best way is to use a method like the one that we proposed. And, it's not the only method of this sort that could work, but it's certainly a convenient one because, like I said, it reduces to a simple formula. The reason a method like that is necessary is because as soon as you say, what is how can I know early on, or as the data is coming in, whether or not there will eventually be a real difference, whether there is a real difference, then you're being adaptive. Like, that's an adaptive question. That's a question that says, I care about making decisions as the data is coming in. And as soon as you're being adaptive, you need to put in some guardrails to prevent yourself from spuriously deciding that there's significant results early on just because of some random variation in the data, like that AA test that I showed you. I think the concluding kind of the coda on the AA testing is worthwhile, which is one of the things that made me so excited to work on this project wasn't just that it was kind of technically interesting. It was cool to combine stats with like a platform that actually got built. So I should add, what I just described is used in Optimizely's core platform by all its customers. So to date it's been used by tens of thousands of customers to run hundreds of thousands of experiments. So it's really been pretty wide-ranging. And then beyond that, what's been great is because it's kind of publicly known, it's also something that many other tech companies have either tried out or implemented internally for their own A/B testing platforms. So I think like one of the things that's important to realize about that is that what we're trying to do in that environment is really change that question from not what's the best way to conclude whether there's going to be a difference or not, but instead just do what's natural. Like, don't think about it, right? So if you use the p-values that are coming out of this dashboard and do what's natural, which is when the p-value is small, you decide to stop, you will actually be making kind of decisions in a near optimal way. Like, you'll be making trade-offs in a good way. So I think that's the job of those of us that build the platforms, is to create an environment where users don't have to reason about a very difficult technical question, like that question of whether I should stop early on. And let me see, there was one other question. Can you scroll up just a little bit? I think there was one on bandits, and that's maybe the one I'll stop with.
Yeah, sorry.
I think it's up on the next page. So maybe I'll just kind of talk briefly about this. So there's a question about multi-arm bandits, and I'm guessing many of you have heard about bandit algorithms as another kind of technique for making decisions over time. There's a lot of value to bandit algorithms. Really what they amount to when it comes to experimentation is what's called adaptive reallocation. So in the experiments that I was talking about, we committed in advance at least to the fraction of incoming individuals who would be allocated to treatment and control. And in bandit algorithm, what happens is you adaptively change whether or not someone gets allocated to treatment and control. A canonical example would be something like headline testing at the New York Times. If I have an article and I have two headlines for that article, if I'm testing out the headlines and I discover one's working better than the other, then in real time I might want to shift more people over to the headline that's working better. One of the problems with this is that while that's great when what you care about is just finding the best thing, it can be problematic if what you care about is inference, which means really understanding why certain things are performing better or worse than others. Because if you can imagine what's happening here, I'm pulling samples away from the lesser performing arms. At the end, what it will mean is it'll be harder for me to determine why those lesser arms, why the kind of lesser headline performed as badly as it did. Was it the wording? Was it the punctuation? Was it the font, right? Like there's lots of different reasons why it might have performed badly, and I won't be able to disentangle any of these effects, using my knowledge of the types of people that have seen it and kind of whether they clicked on it or not. So inference is the procedure of understanding, and bandits are a procedure of optimization. What I love about modern data science is it's kind of equal parts understanding and business optimization. What I often am fond of saying, and maybe this is the last comment I'll leave you with, is that people often want to be optimizers prospectively. So when you start an experiment, people say, just find me the best thing and do it. But they often want understanding retrospectively. And that's because when you try to find them the best thing and do it, and it's not what they thought would be the best thing, then they want to know why. So VP comes to you and says, hey, I think this is going to work well. Go find the best thing and do it. You run the test, you find the best thing, and it's not what the VP said would be the best thing. Now they want to know why it wasn't the best thing. So one of the challenges, I think, in business optimization and inference is exactly to balance optimizing with understanding so that you're able to answer those questions after the fact when they're asked, and yet you know that you made the best decisions possible. So let me leave it there. Thank you all. It was a lot of fun, and hopefully I'll see some of you in 226 in the fall.
Okay, Ramesh, thank you again for the talk, and also those really helpful, detailed answers, and some great practical examples as well. Thank you to everyone who attended the webinar and sent in questions. I hope you're going to be able to join us again for a future one. Enjoy the rest of your day, or depending on where you're joining us from, have a great evening. Thanks.